Yeah.
Okay.
Let me
Yeah, I learned it. No, where? YouTube. Try me. So yeah,
Okay.
good.
I'm at the word games, but I wanted to put the word games.
Uh,
Sorry, no.
we have
Sorry, no.
we have some echo. Is maybe in from your side? Echo?
No,
I think that.
don't think so.
Okay, so now it's okay.
Mhm.
But we, someone is talking. Okay, good. So welcome everybody to this webinar by Dr. Susan Ip-Jewell. And this is the fifth preliminary webinar of our preparation for the Congress of Space and Astronaut International, the fourth World Congress of Space and Astronaut International that will take place next year in end of June 2026. So we have invited many professionals and experts of several disciplines in the frame of space, of course. And today we have Dr. Susan Ip-Jewell. So the abstract of this webinar is the next era of human exploration demands a profound rethinking of how health, medicine, and consciousness are sustained behind Earth. Space pharmacology and medicine have emerged as key disciplines focused on understanding and mitigating the physiological, psychological, and molecular challenges of life in microgravity and other isolated, confined, and extreme environments. This evolving field integrates biomedical research, analog astronaut missions, and intelligent technologies to operate adaptive health systems that can support long-duration spaceflight and planetary habitation. Recent developments emphasize the convergence of computational modeling, biotechnology, and human-centered design to enhance therapeutic precision and resilience. By leveraging simulation-based studies and controlled terrestrial analogs, researchers are advancing predictive frameworks to optimize treatment safety, pharmacological performance, and behavioral health management under altered gravitational and environmental stressors. In parallel, the emergence of ethically aligned intelligent systems introduces a compassionate dimension to human-AI interaction, supporting mental well-being, decision-making, and team cohesion in remote or autonomous mission settings. This holistic approach, Space Health 4.0, represents a transformative model for medicine and human adaptation. It bridges biological science with cognitive and ethical awareness, aiming to ensure the sustainability of human life and consciousness as civilization extends into new frontiers. Ultimately, space pharmacology and medicine embody a renaissance of scientific and humanitarian innovation, fostering technologies and principles that will safeguard both astronauts in space and communities on Earth. This is Dame Commander Dr. Susan Ip-Jewell, MD, DCEG, DOD, is an internationally recognized pioneer in human spaceflight, space medicine, and analog astronautics, with over 2 decades of leadership advancing humanity's expansion beyond Earth. She serves as CEO and co-founder of Mars Moon Astronautics Academy and Research Sciences, co-founder and chief medical and innovation officer at VASTX, Virtual Astronaut Simulator for Therapeutics and Exploration, and founder of Avatar Medic, integrating AI, XR, telemedicine, and digital twin modeling to revolutionize astronaut training, healthcare delivery, and adaptation in extreme environments. Dr. Ip-Jewell is a NASA Trish Frontier Fellow, three-time finalist in the Humans in Space Challenge and recipient of the Sir Arthur C. Clarke Award from the British Interplanetary Society. She holds 2 knighthoods as a Dame Commander from the Royal House of Georgia and the Royal House of Montenegro, honoring her humanitarian service and advocacy for justice, equality, and education. A vanguard in space medicine, neuroethics, and ethical AI, Dr. Ip-Jewell is dedicated to promoting diversity, equity, inclusion, and accessibility, DEIA, in space exploration and STEAM education worldwide. Her visionary leadership continues to inspire future generations of explorers and innovators to build a sustainable, compassionate, and multiplanetary human civilization. So, Susan, the floor is yours.
Well, thank you so much, Adriano, for that really long and extensive intro. And thank you for inviting me to present today. And so let me try to share my PowerPoint slides. As always, we're on Zoom. So
Yes.
what happened to my PowerPoint slides? Oh dear, hold on one second. That's not, I had it open. Yeah, I did have it open, promise. There you go, right? Now I have to find it. Let's see what it is. I had it all set up. And now it's disappeared. All right, give me a second.
We always fight with technical problems every time.
Okay, I found it. So sorry about that. It closed up on me. So
Never mind.
let me share this now and let me know if you can see my slides.
Yes, I'm seeing your screen.
Slides.
Okay.
Okay, good. All right. Well,
Maybe.
today, can you see?
Okay.
No, see?
Yes, you're full screen now. Okay.
Okay,
Go ahead.
good. Fine. All right. Thank you. So thank you so much, Adriano and SRI for inviting me. And I'm very excited. Obviously, I'm also part of SRI community. But today, really, it's just going to be a very high level, brief overview of where we're heading in terms of space pharmacology and space medicine. Obviously, those two are very much interrelated and integrated. But really, if you are looking to actually become multiplanetary, we need to really discuss how do we take care of the humans in space. And obviously, when we come to medicine, how do we take care of these injuries if there's medical conditions, because space is very challenging. And then on top of that, where do we also look at pharmacology in this whole construct of multiplanetary settlement and permanence in space? So that's what I've been doing in those different areas, and so I will talk a little bit about this subject matter, and let me try to also see if I can do this. Okay, I will put. All right. So, with that said, my talk is on space pharmacology and space medicine, and we've been testing some of these ideas in our analog astronaut in person as well as virtual missions under MMAARS. So, with that said, let's move on to the next slide. Why is it I cannot on to the next slide? Why is I'm having so much difficulty today? Let's move this. Okay, there we go. All right. So, okay, first of all, let's talk about what is space pharmacology, right? So this slide actually defines the term space pharmacology. And it's the study of how medicine behaves in a unique environment of space in altered gravity, because humans are going to be subjected to multiple challenges: exposure to radiation, disrupted circadian rhythm, the psychological, the physiological, the philosophical, the wellness and well-being are altered in a very extreme environment like space. So if those fundamental areas are changed, the anatomy as well, then obviously drugs that we take into our body are also going to be changing the kinetics, the distribution of the drug, how the drugs are metabolized and excreted, because our pathology is going to change as well. So that's why it's important to actually study space pharmacology, because these are shifts that create serious challenges, right? In terms of achieving accuracy and safe drug dosing when we're on a long duration space mission, and one day when we actually live on a planet surface, because even on Moon and Mars we are living in altered gravity, because our body to date has only evolved under 1G, which is on Earth. So we need to look at space pharmacology. We need to look at different ways of creating drugs. This is where 3D printing of drugs and 3D bioprinting of drugs and organs, to do the research to say, how do drugs change their kinetics when we are in these altered gravities, right? So, and this is going to actually advance the way that we're going to look at precision medicine and predictive medicine. And one day we definitely need to look at precision medicine. So what is pharmacokinetics in terms of pharmacokinetics here on Earth and in space? Well, K, which is short for pharmacokinetics, is a critical research priority for spaceflight in microgravity, right? The body no longer behaves as it does on Earth. Fluid distribution shifts upwards. It's a very strange phenomenon, but when you go into microgravity, all the fluids in your body moves from your lower extremities, your legs, all the way up to your upper part of your body, which is kind of unique for microgravity environments. So that's going to affect your cardiovascular performance. Those are changes, respiratory changes as well. Metabolic pathways are altered, enzymes in the body that breaks down food, breaks down drugs, is going to change. So these are going to directly affect how drugs are absorbed or distributed or metabolized and excreted from the body. So these, what we would consider physiological changes, can significantly impact drug efficacy, safety, making standard Earth-based dosing unreliable. So we need to understand these altered kinetics or pharmacokinetics. It's so essential so that we can develop safe, precise, and space-specific therapeutic protocols that can protect the astronauts' health during these long-duration missions. And so that's why it's so important to study pharmacokinetics, which is basically how the drugs work in the body when we're in different environments. So with us, one of the new companies that we formed that actually won the Humans in Space Challenge this year is VASTEX. And VASTEX actually stands for Virtual Astronaut Simulator for Therapeutics and Exploration. So we're pioneering the very first AI-driven digital twin of an astronaut that then we can use to explore through this adaptive AI precision model, to be able to look at precision drug dosing, and also be able to predict if there are changes in the anatomy, the physiology of the astronauts. We can then do predictive analysis of what we would say how the drug will behave, and therefore it will allow us to do precision dosing. That is kind of where this platform of using these technologies is going to enable us to do that. I mean, it's pretty powerful technology using AI-driven digital twins, right? So VASTEX is actually going to be testing its first model in our MMAARS analog missions, in our multi-fidelity and multi-habitation analog missions in person, as well as our virtual training next year. So it's going to be exciting. And then we're the data we collect will be extrapolated, collated to go into parabolic flight, and then eventually, hopefully, to microgravity platforms. So this whole idea of a digital twin AI-driven PK, PBPK, right, is going to ensure safer, more effective treatment strategies when we go into extreme space environments, right? So VASTEX actually represents the future of adaptive space medicine, and it's going to allow us to empower human exploration through intelligent, data-driven decision making and therapeutic optimization. And those are actually critical factors and what we're empowering in the model and testing to allow us one day to be autonomous. So when you're going to go deep space or live on a planet surface permanently, you have to think about being autonomous and tethered to Earth. You won't have the ability to have full-time medical pharmacologists, space medicine, healthcare providers for the crews or for the astronauts, right? So it has to be onboarded in some way in a system, and AI is going to allow us to develop these models and integrate into the autonomous systems that were built either into the spacecraft or into the habitat. Oops. Next slide. So now we're going to talk a little bit high level. What is space medicine, right? So this slide actually defines space medicine, and it really is the approach of the holistic paradigm construct of preventative health ecosystem that goes way far beyond emergency care. Right. So in extreme space environments, the astronauts actually face progressive challenges such as bone loss, muscle atrophy, immune suppression, neurocognitive changes, and much more challenges that the astronauts face. And if the longer they're in space and the exposure to radiation, ultragravity, the more challenges that the body is going to be subjected to. So we need to actually develop countermeasures to these problems before we can actually say we can live safely and thrive in space, right? So with that, space medicine integrates physical, psychological, and behavioral health strategies that will maintain resilience and sustain optimal performance over long durations in space. So combining preventative monitoring, mental health support, and adaptive interventions, this approach in space medicine actually ensures that astronauts remain healthy, they are functional, and they're mission ready. So forming the basic foundation, this holistic approach for future safe, sustainable health presence beyond Earth is kind of where I want to go and where space medicine should go in to be able to help us thrive in space, right? So that's really what we're trying to do in space medicine in many different areas. So with that said, what is also AI-driven digital twin in space medicine? What is a digital twin? So in this slide, you can see there's a human astronaut, then there's a replica of a digital twin of the astronaut. So basically, in the digital twin, we have coded every single system in the human body into the digital twin. And that is literally is what a twin is, right? So, but not only is it a digital twin, we've developed the AI-driven digital twin. So there's the integration of the AI, artificial intelligence, that will be trained on the astronaut over time. And the more it's trained on the, physiological, psychological, all the different aspects of how the astronaut behaves, the pathological changes and physiological changes, it will train its own digital astronaut and with the AI. So it's going to evolve with the astronaut and get to know more about the astronaut's biopsychosocial factors, physiological factors, and so on. So the AI digital twins will revolutionize how we actually take care of astronauts, the healthcare of the astronauts, right? So basically, as I said, a digital twin creates a living virtual counterpart of the astronauts. It's continuously updating with real-time physiological, psychological, physical data. So this then will allow precision health modeling and then will enable a personalized adjustment to treatment. that will respond to changing conditions in space, right? And this will then allow us to have predictive pharmacokinetic simulations. So we can then anticipate how medication will behave before they're administered. And that will reduce risk and side effects and enhance therapeutic accuracy. And that's really the critical part of why we want to incorporate these technologies. So basically, an AI digital twin technologies will shift space medicine from a reactive treatment to proactive precision-based care. And I think that is the new construct paradigm that we will head to when we integrate these type of technologies. And I think that's the most exciting part of actually when you're talking about technology, you have to say, can it actually help improve the state of the art in that field? And definitely with AI, and with digital twin and autonomous robots, humanoid robots, when you converge all those technologies, for example, it literally will give us that construct paradigm model where we don't need to be dependent on Earth or dependent and be tethered to Earth, right? With regards to medical care and therapeutics. So another great technology, obviously, is 3D printing. And in this case, we're looking at 3D biomanufacturing and regenerative medicine, right? These technologies, like the ones I just mentioned, literally will transform and is currently transforming the healthcare, and particularly in space, right? So by enabling because these technologies will enable the creation of living systems beyond Earth. So, like, for example, through bioprinting, we can generate tissues and organoids for both research, R&D, research and development, for being able to test emergency medical interventions, while on-demand pharmaceutical production reduces the dependency on Earth. So the idea, right, the vision is that now when you're in deep space and you don't have a supply chain, you're able to produce either from stem cells or in your greenhouse biodome, produce the plants now that have medicinal properties. Now the vision is you can harvest plants or with the stem cells, cultivate the stem cells, whichever from the plants that has medicinal properties, and you can from that source, you could use it to actually 3D bioprint medicine, bioprint organs, bioprint tissues, and do research. But that allows you, yet again, that whole concept, no supply chain, being totally independent and autonomous, right? So that's where it's exciting as well, because you can use these models and technologies to regenerative medicine, right? So for example, you can do R&D and with the organs or the tissues, you can do research in wound healing, tissue repair, long term, and that will enable you to say, all right, that will address some of these issues of if you have injuries when you're in astronaut space and you need the medical supply, you need the organs, you need the skins, somebody could get burnt. So now you can actually print the skin and, be able to heal the wound with the 3D stem cell, printed skin, for example, right? So this actually is a really important future technology, or not future technology, it's a technology we're doing now, but to integrate into deep space mission. So genomics and precision medicine is another area of space medicine, specific area that we absolutely need to look at. And because, when we explore genomics and precision medicine, we are also advancing our understanding of human adaptation in extreme environments like space, right? So by monitoring genomic and epigenetic changes, we can identify biomarkers that reveal both resilience and vulnerability to the extreme conditions of spaceflight. And we all know that exposure to cosmic radiation is definitely going to alter our genome, our genetic material, the DNA. There's going to be a high risk of mutations. So how do we address that, right? So I think to study these two areas is very important. Genomics and precision medicine, they go hand in hand. So when we do and collect this data and we conduct this in space, this will actually allow us to design tailored health strategies that can be based on each astronaut's unique biological profile, their biopsychosocial profile, their family history of medical conditions, and that is really important, because then it literally will shift us from reactive care, which I said, to preventative, personalized medical care. And that's where we're heading. This whole construct of reactive is going to take us to personalized, preventative, predictive medicine. So the outcome is a genetically informed spacefaring population, right? That's optimized for safety, for performance, and long-term survival beyond Earth. And also doing genomics in space, um, is also going to help us understand, to come up with new cures, new therapeutics, new methodologies for helping improve the medical conditions on Earth. So Space MedTech Ecosystem, what do I mean by that? This slide actually illustrates how a fully integrated medical technology ecosystem will enable autonomous healthcare in future space settlements, right? Through wearable biosensors, continuous monitoring, real-time physiological data can be captured, analyzed by the AI-assisted diagnostic and decision support systems, right? You have telerobotics and autonomous medical interventions. This will allow us to offer rapid, precise care, even when human specialists are unavailable. Remember, in the early days of planetary settlement or deep space, we're not going to have all the specialist healthcare on board. We will have it actually trained into either the humanoid robot here you can see, or integrated, all these specialists integrated into the AI system that's part of the computer system of the spacecraft or the habitat, right? Or the space clinic, space hospital eventually, right? So that's where really why these technologies very important to think about and integrate. So like smart habitats that are embedded with health AI networks that can create intelligent, responsive infrastructure that can support crew well-being, there's the crew performance and safety, right? So together, these technologies can form the backbone of a very resilient, self-sustaining medical system for long-duration human presence in space. And that is why it's pretty exciting nowadays. If you have a technology and you can find a right application for it that can improve quality of life and enable to help us to thrive in space, that's where I'm excited about these technologies. So only a few more slides, but I think this is important. Enabling multiplanetary settlements, right? So in terms of these two areas, pharmacology, space medicine, preventative health, is enabling multiplanetary settlement. We must really emphasize that sustainable human health is the cornerstone of a multiplanetary civilization, because we're not going there with just robots. I mean, a part of why we want to become multiplanetary is because we are the explorers. We have an innate drive as humans to want our curiosity, to want us to go beyond what we already know. We are curious about the unknown. So when we want to go to space, we want to live in space. We want to live on a planet's surface because of our curiosity, right? So there's a drive for us to want to do something that is unknown, and space is still the unknown. That's why we are fascinated by space. But if we're going to do that, we need to think about humans in the loop. We need to take care of the humans. That's number one. We can always build the technology, the rocketry, and all this. But if we put humans in the rocket, humans in the spacecraft, humans in the space habitat, they should be priority. We should be priority. So all these technologies will enable us to take care and put first priority the care of the human astronauts, right? So to establish a long-term habitat on the Moon and Mars, the crews must achieve medical autonomy, reducing resilience on Earth-based healthcare systems, right? So through this integrated space medicine with the AI support, advanced biomedical technologies, we can definitely strengthen biological sustainability. We can enhance the ecosystem resilience and optimize human performance in extreme environments. So, by prioritizing preventative care and adaptive health strategies, we can create the foundation for the thriving off-world communities. So I'm simply putting forward that healthy humans are essential to building resilient and sustainable space civilizations. If we don't have that as the fundamental base to build on, we won't be able to manifest this vision and actually be successful in terms of becoming multiplanetary. So this one is also important: ethical and human-centered AI in space medicine. When we are talking about humans in the loop at all times, we always have to look at the ethical and the moral aspects of that, right? We're not just talking about technology, we're talking about the human sentient being. And so, what do we do? How do we conduct ourselves when we're using humans in the loop? We need to look at the moral aspects. We need to look at the philosophy. We need to look at the ethical aspects when we have humans in the equation. So this slide actually highlights that critical role of ethics, ethical human-centered AI in safeguarding the astronaut well-being, their mental health, their philosophical health, spiritual well-being, their physical health, right? So as the artificial intelligence become more integrated in space healthcare, it must be designed with empathy, with transparency, and strong ethical guardrails to protect the human cognition and their emotional stability. We've got to be able to have a benevolent Hal. If you know Hal, that was in Space Odyssey, that movie, he was programmed to be malevolent. To me, he was a bad actor. Why? Because he was programmed in this movie to only have the directive of mission success. It wasn't primary directive, wasn't programmed for safety of the humans. That's where it went wrong. And so we need to say humans come first. So if we bring any form of AI systems into the loop where humans are involved, we have to put the safeguards in. We have to say its priority, its directive is to the safety of the humans, right? So we need to also look at compassion intelligence. Compassionate intelligence, besides empathy, will ensure that the AI will support rather than override the human judgment, right? It can foster trust if we build this compassionate, empathetic, intelligent AI, build trust, accountability, and psychological resilience within the crew teams and the crew mission. So it's important to prioritize ethical deployment, right? Enhance mental health, create a supportive environment so that essentially it will enable us to thrive in space. So what's my future vision for thriving beyond Earth and to permanently live in space? We presented a vision where space medicine becomes a cornerstone of humanity's evolution beyond Earth. So, as planetary settlements emerge, that's the vision, space medicine will support sustainable life, while AI enhanced biology enables humans to adapt to extreme and unfamiliar environments like extreme environments. So integrating health ecosystems across celestial bodies will ensure resilience, longevity, and optimal performance. So actually, when we talk about this paradigm vision that we want to manifest, this is not merely about exploration, but actually, truly, it's about inner transformation, the evolution of our humanity to that next place, right? So evolving into a multiplanetary species capable of thriving with purpose. The future of space is not just about rockets and habitats, but it's really about preserving life, not just human life, but all forms of living life on Earth. We want to bring that along with us too, right? The whole Earth biome is also part of this construct that we need to think about. But also it's about preserving consciousness, our human consciousness, that nuance of our humanity that we need to really deeply think about and say, can we bring that with us? We absolutely need to. Can we put that into the AI, Maybe it's not artificial intelligence. Maybe eventually in the future, we can create authentic intelligence, something that has the humanoid nuance of what it is to be human, that humanness, that humanity of us. That's very unique to our species, right? So the future of space is not just about rockets, and as I said, or habitats, but it's about preserving life, preserving consciousness, and our shared human destiny among the stars. So I want to say thank you, and I will stop sharing. And you can reach out to me here if you want to talk more, learn more about what we do under MMAARS. And thank you so much, Adriana.
Thank you. Thank you very much, Susan. A beautiful presentation as always. Thank you so much for giving us awareness and consciousness of what we have to face when we start going into space. And this, of course, you're talking about, let me say, a kind of a transition
Mhm.
between the dawn of the space age, because we are in the down in the very beginning, or let me say the prehistory maybe, because we are talking about exploration and starting to go outside and try to live on planetary surfaces or space habitats in free space and so on. And we are going to try to build the conditions for civilian communities taking place in space communities, where, of course, the environment and everything should be as beautiful as possible
Yes.
in other terms, in terms of gravity, possibly equal to 1G, and protection from cosmic radiation and everything. So to be in condition where we don't need pharmacology in the first in the normal living. And pharmacology, of course, we will need pharmacology when we get ill, when we have, and then we have to, of course, all the medicine that you illustrated is very important also for let me say, the normal life during the. But however, okay, of course, I have some questions, but I want to give priority to the questions from the audience. We have some questions from Dinis Ribeiro. Dinis is our member in Portugal. Is a researcher and okay. He is asking. There is bibliography about hyperbaric medicine. Are there studies about using microgravity and hyperbaric conditions at the same time? This is the first question.
Yes, there is. There's a lot of work. There's a lot of work and publication and research in hyperbaric medicine. In fact, there's several organizations that is specifically about hyperbaric medicine underwater. And I think I don't know exactly top of my head what they're called, but they're pretty international. They just partnered with the Aerospace Medical Association, and so the upcoming conference next year, I think it's usually in May, they have an open call for abstracts in hyperbaric medicine. But with myself, we are very interested in these because hyperbaric medicine or hyperbaric pressure or high altitude and parabolic flights are proxies or substitutes that kind of be analogs of microgravity without actually being in microgravity per se, right? Because under those extreme conditions, your body also has actual not physical and physiological changes, and so you can use them, as I said, as proxies. And we're literally MMAARS are going to test VASTEX, this model, right? This AI-driven digital twin of the pharmacokinetics next year, and doing a series of hyperbaric analog missions. So we're going to live a couple of crews that we select. Analog astronauts will live underwater off Florida Keys because there's an underwater habitat there, and we will be testing their physiological, psychological, and also their physical changes under hyperbaric pressure, and then looking at some of the drugs that we will be testing through VASTEX. So yes, absolutely. I think And you know, when you think about our planet, the ocean, and we're basically mainly water, right, Adriano? And a very, you know, I think it's like 80% of Earth, if not more, is actually water. And a vast area of our oceans, deep oceans, we still haven't actually discovered. And so I think also it's very important to do more underwater missions, to do more research for the human body underwater long term, because water is an analog, quote unquote, of microgravity as well, right? So that's why we train the astronauts, NASA does, at the neutral buoyancy lab, right? Which is a huge swimming pool, and they've got a replica model of the ISS. And because of that, right? So yeah, I think definitely. And if you're interested in what we're doing next year, yeah, reach out to me. And because we are starting to select very highly qualified crews, analog astronaut crews, or explorers and undersea experts, you know, divers to join our mission.
Thank you. And you are touching a point that is very interesting for Dinis Ribeiro, because he made a beautiful paper on the subject of water in space. He sustained that we will need a large quantity of water in space. And of course, that will be possible in some on-air model, big rotating habitats where the Earth and the Earth biome can be reproduced in this artificial construct, including water, big lakes and so on. So it's very water is very important in order to for our health and also mental health, of course, because they are strictly connected. So next question comes from Werner Grandel. Werner Grandel is from Austria. He is another of our members, also board member in SRI. And he is an architect. He designed rotating habitats and also industrial plants in space, in free space. And but in this case, he is asking: are we moving towards superhuman beings or transhumans by establishing digital twins? And also, bioprinting seems to lead us to superhuman. What do you think about?
Well, it's how you define superhuman. I don't say it's superhuman. I say these technologies now, at these early days, is more enhancement. It enhances our humanness in terms of our capabilities, right? For example, you know, when we build exoskeletons, right? So it helps obviously for people who are paralyzed and disabled, physically disabled, and helps them to move. But even for a healthy person, if you wear exoskeleton and it's 3D printed, now you can get those 3D printed, it actually allows you to lift heavier weights if you can't do it, to walk longer, walk faster. So, I mean, that's a good example of what technology is. So it's not so much to me of becoming a superhuman. It's becoming more, these technologies help you become augmented, enhancing your human capabilities. That's how I see it. So the digital twin is very important because and when it's AI driven, it's because you want to keep training and training, and it becomes evolve, matures with the system, or in this case, the astronaut. But the point of the digital twin is that you're literally replicating a mirror image of that model system. So in this case, it's a human being. So you can,
Yeah.
for example, I can have Adriano and I can create a digital twin of Adriano. What do I mean about that? It means that I'm going to create a simulation, a computerized at this point simulation of Adriano with all his biopsychosocial,
That would be great.
all his, yeah, all his systems, his anatomy. It's in a computerized. That's what a digital twin is, and in this case, a human digital twin. It doesn't mean I can that's going to transform into be a superhuman. It's how you apply it, right? So in this case, with drug discovery, you know, Adriano's different from me, my makeup, everything. So a drug that I take, maybe, you know, it's going to act differently, how it's clear, how it's metabolized. When Adriano takes it, same dose. When I take it, maybe he might have some side effects because maybe he has comorbidity. He has some other medical conditions that I don't have. I'm just giving you a simple example, right? So where the digital twin comes in this particular case is that we modeled one for Adriano, we create one for me, and then we say, okay, let's have the same dose of a drug. And in this case, let's say, I don't know if I should use acetaminophen, but anyway, let's say it's Tylenol, acetaminophen. And then we can say, oh, just say, maybe Adriano has liver enzyme issues. So it's going to cause different kinetics of that drug. So now
Yeah.
we can say, okay, Adriano, maybe we should increase the dose. And Susan, you seem to be fine. And so that is giving you example of what the technology is doing, right? In terms of creating that digital twin, because now you can push it through the digital twin before you give the actual medicine to the human person, because then you could see through the digital twin what the effects are, how ethical, the efficacy, the toxicity, the clearance, and do we need to increase the dose? Do we need to reduce the dose based on all these other parameters, right? Which I just gave you,
Yeah.
for example.
Yeah.
See, that's why
And
it's so interesting, and it's really important. And it really literally is going to advance the state of this field of precision drug dosing and predictive medicine.
NASA tried to do something similar with the real twins. When astronaut Scott Kelly stay 1 year on the ISS, his brother, his twin, Mark Kelly, is an astronaut too, but he's still on Earth, and they were able to make studies about differences between staying in microgravity for 1 year and staying on Earth, and comparing two very similar biological systems because they are twins. So yeah, there are studies that's very interesting from this point of view.
Yeah, but I want to say, yes, absolutely. That's the twin study, not digital twin study. And you need to have twins. So, thank
Yeah,
goodness,
of course, of
there was
course.
twins, right? Now,
Yeah,
not
if you
everybody
have
has a twin.
yes, yes.
Not everybody
If
has a
you have a
twin. Now,
simulator, if you have a
we have
human simulator, by the way,
right, but
where you can
exactly.
test something and having the response from the simulator that could be very, very similar to the real
So,
person, because they are modeled, the simulator is modeled exactly on the same
yeah,
model of the
person,
real person. Yes,
right.
it's
So let me say, with the Kelly twins, it was great, and of course, one brother was on the Earth, was the control, the other one that went actually into microgravity, was the subject arm. However, now that's because they happen to have a twin, but now everybody can have a twin, and it will be exactly like
yes, yes.
you. Versus
Right.
there would be, even if they were twins, the Kelly twins, I'm sure they had some variations, because of their backgrounds in when they lived in different environments. Maybe they have different diet, whatever. So there is variations. So it's not exactly that they were exactly twins per se. Now when we build a digital twin, it will be exactly like you, because it's going to be trained exactly. It's like a mirror self of you. See, now everybody, well, we that's where we're going, right? Well, eventually you would get your own digital twin, a mirror exact replica of yourself, and you can do all these different tests and studies and get to know yourself without
Yeah, that's
actually
great.
putting drugs into you, so in terms of digital twin in research, because I did clinical research, drug discovery at NIH. I mean, now we don't need to have humans or animal eventually, right? We can eliminate the ethical and moral aspect of actually using human subjects, which is what we had to do, terminal patients we had to use, right? And animals. Well, in the future, in the near future, the digital twin will eliminate the use of actual animals for testing and humans for testing. And
Yeah,
I think
also,
that's a better way forward,
yeah,
philosophically, just as ethically, morally. I just think this is the better way
sure,
forward.
sure.
See,
Great. We have, okay, another question from Dinis Ribeiro is about the human lungs and the human lungs and exposure to lunar dust. What kind of countermeasures are being considered? You know that the lunar dust is very dangerous for lungs because the granulometry is very, very thin, and if you breathe it, it will be terribly dangerous, harmful for our lungs. But
Well, yeah,
I'm afraid
that's
the
not.
pharmacology cannot reply to this problem. Maybe we need to make a safe separation. I mean, in a lunar habitat, there we will need a very hard intermediate room in order that I can enter and completely wash my suit, my space suit before.
No, so there's better ways, there's better preventative ways. One is physical countermeasures. So you actually, which, NASA does, and you could see it, the spacesuit, actually, that's when I came out of this 21-day analog missions at the University of North Dakota at their habitat. They have a rover, and then they have the spacesuit that's attached to the back of the rover. So you never, when you wear this, it's called donning, when you don your spacesuit, when you're getting it, you're not outside, right? You're actually inside, and you climb into the
I
suit.
see.
The suit is actually attached to the rover. So then once you're in the suit, then you detach yourself from the rover. So you're never at any time
Okay, so
exposed
you leave
except
it
for the suit.
outside. You leave it outside.
Yeah, the
spacesuit.
suit is outside or it's attached
Great.
to the rover. And you as a human, so your suit never comes inside the habitat, right? So it's called backwards forwards contamination. There's a lot of studies, we do that too, and we also did that in this 21 mission. But the point is, so forwards and backwards contamination is something that you really need to be very cognizant about, right? You don't want to bring in all that contamination, all the toxicity. So attaching the spacesuit outside, exterior, and the astronauts just climb into it, then they do it, and then when they do their EVA, when they come back in, they actually attach themselves back, and then they climb out of the suit, right? Now that is the physical way. Another way is more chemical, or let's just say there's another way. I don't know the research. I read it recently, but there's a research team that's looking at magnetism and being able to build material that has magnetism that can repel some of the toxic elements in the lunar or Martian regolith. Right now, that's interesting, isn't it? So now you won't have, because it's static electricity, that seems to be, attracting it to the suit. So now if you have material that it has magnetism or some form of magnetism built into the suit material, it can repel a lot of this metallic, components in the regolith. Another one is obviously looking at chemically removing the toxicity from the regolith, and there's research doing that as well, right? So those are just some of the ways in terms of how you can prevent backwards and forward contamination, into the habitat, which is what we're doing as well in these analogs, right? And then looking, because obviously it affects the health of the astronauts. And with the ISS, obviously they're not on a planet's surface per se, so they don't have to deal with regolith, but so but the ISS is pretty contaminated, I would say, right? It's got molds and everything growing on it. So that's not healthy to human health too, right? Being in an enclosed environment. So it's actually a big problem that we have to, so maybe redesign, for example, redesign the structures, the architecture of the habitats that has incorporated either these magnetism, right, materials, or something that is able to scrub or remove or not attract, the regolith being stuck to the architecture or to your clothing. It's interesting, right?
Okay, so we don't have other questions so far. So if we don't have other questions, I think we can maybe close this session. That's
Sure.
very, very interesting, and we hope we can
Yes.
do another one soon.
Sure.
And
Yes.
okay, so thanks
So
everyone.
let me just say that if you're interested to reach out, to a lot of the work that we're doing under VASTEX and
Sure.
MMAARS, you can go to our website at VASTEX, which is, www.vastex.space. And then MMAARS, which is Mars Moon Astronaut Academy and Research Sciences, you just go to MMAARS, MMAARS.com. And we actually have several analog missions, virtual as well as in person, coming up to test a lot of these studies and VASTEX as well next year. So yeah, thank you. I just want to also call out, Space Renaissance International SRI, which I'm being part of with Adriano, who's CEO, founder, amazing in doing great work. And I really do also want to say the spiritual health and understanding philosophy, definitely really understanding the overview effect of the human body in space, that it's very transformative. I think very much more, if we were to survive, have a better way to survive is to understand and go into our inner space journey and stand self first before we even want to go out into space. I think that's critically important. So what SRI is doing is really amazing, and it's really important part
Thank you.
of being an astronaut.
Thank you very much. And I would like to close this session inviting you to visit the website of the Congress, of the fourth SRI World Congress. I have posted the link in the chat, in the YouTube chat, and also the link to the website of the Congress. That's our call for papers. And also I have posted the link to the form where you can submit an abstract for a paper, if you like, to present a paper during our Congress that will take place along 5 days. So we will have time for several tracks, sessions, one on technical, scientific items for. So you know that the title of our Congress is Quality of Life on Earth and Beyond. So we are trying to focus all the conditions that will allow civilians to live and work in space. And this includes, of course, a lot of topics, scientific, technological, psychological, philosophical, and many, many topics, living in space conditions, the space habitats, the beautiness that I was mentioning before, the redundancy of the life supporting system. This is a condition that was not very much considered during the exploration age. Because on the ISS, just to make an example, the life supporting systems are dimensioned for 7 people maximum. And in some times there were 10 people on board with big problems about carbon dioxide breathing and so on. And there were only 2 air recycling systems. So if in the worst condition that both are in fault, then that will be no way to continue living for resident people there. So we have to think in terms of a very much bigger redundancy when we think about building civilian habitats and communities and so on. So we have to completely change our minds to trying to escape from the let me say, the economic consideration that we want to save money and so on. No, we don't have to save money when we design for space. There in space there is abundance of resources, so we are not constrained to be greedy and attached to not spend 1 cent more. No, we have to spend more, because only having a big redundancy we can be safe and confident and to be peaceful and work and be sure that we have a future and so on. So, okay, so this is just one of the topics that we will discuss, and we invite everyone to think about conditions of living in space and to submit their abstract for papers in one or more of the sessions that we have written in the call for papers. So, okay, so thank you very much, everybody, for joining us, and see you next time.